Today's lesson is area of triangles in trigonometry. We're going to go through a progression of 10 examples as we discover a new strategy, technique, formula for finding area of triangles. We're going to warm up with example 1, which is pretty straightforward, classic right triangle, and we'll use our reliable formula, area equals 1/2 base times height. This formula comes from the area of a rectangle divided by 2, since right triangles are half of a rectangle. If we look at the picture, we clearly have the height and base labeled. The height has a value of 6 and the base has a value of 2, so we're just going to fill those in to their appropriate places. Then what we want to do in the next step is you have to just watch out for a silly error, but some people distribute that 1/2 to the 1 and the 6. We don't distribute unless terms are separated by a plus or minus sign, so please definitely watch out for that. You could just multiply the 2 and the 6 first and find the area is half of 12. And since half of 12 will give us 6, we can just write that the area of this triangle is 6 units squared, or square units, whichever you would prefer. Let's take a look at example 2. Here is a really basic example of a problem where you're not given a picture. If you had a ruler, a straight edge, and a bunch of props, you could have created this triangle if you would have liked to. But I'm really hoping at this point in the curriculum that if you saw these 3 numbers, 5, 12, and 13, you would either know to investigate and check if this makes a right triangle or not, or maybe you would just use Heron's formula. But I think that this is pretty easy to recognize that it's a very famous Pythagorean triple. We see 5, 12, 13 all the time, and we also see 3, 4, 5 all the time. If these are the numbers that represent side lengths of a Pythagorean triple, that would mean that 13 is the hypotenuse. Therefore, the 5 and the 12 must be the legs. If 5 and 12 are the legs of the triangle, they must be perpendicular to each other because it's a right triangle. So think about that for a second. It should make sense. If they're perpendicular to each other, that qualifies them as a base and a height. So once again, without a picture, but with the knowledge that this is a Pythagorean triple and therefore a right triangle, we can still rely on our area equals 1/2 base times height, good old reliable formula. This time when I multiply, I'm going to approach it slightly differently. Since I have 5 and 12, maybe, I always forget what 5 and 12 are. Is it 60 or 50 or 72? I get confused. If you don't feel like multiplying and making things bigger, what we could do is take half of 12 since it's even, and that's pretty easy to do. Half of 12 is 6, and then just finish with 5 times 6. 5 times 6 is 30, so our final answer for the area of this triangle is going to be 30 square units, or 30 units squared. Let's get started on example 3. Example 3 is another right triangle, so we can still implement our good old reliable area equals 1/2 base times height. Base and height are always perpendicular to each other, so I'm realizing I'm missing one of those lengths. Fortunately for us, we have a right triangle, and to find one missing side of a right triangle is not really that big of a deal. We should all know what formula we need to use to find the missing side of a right triangle when you have the other 2 sides. We're going to use, you guessed it, Pythagorean theorem. Once we have that missing side, we'll fill in our values to the formula, area equals 1/2 base times height, and call it a day. If our answer has a radical in it, we have to be sure to simplify the radical. A squared plus B squared equals C squared. We'll fill in 7 for A and 18 for C. 7 squared plus B squared equals 18 squared. 7 squared is 49. 18 squared is 324. So we'll have 49 plus B squared equals 324. Our goal is to solve for B right now, so we're going to subtract 49 from both sides, and we'll have, for our next line, B squared equals 275. Now, 275 is not a perfect square, So when I go to take the square root of both sides, I'll have radical 275, and I'm going to need to break this number down so I can try to figure out the simplified version of this radical. 275 ends in a 5. In fact, it ends in a 75. That means not only is it divisible by 5, but it's actually divisible by 25, which is a perfect square. If we think about quarters, 25 cents are in a dollar, so 25 times 4 is 100. That means that 25 times 11 will give us 275. So 5 times 11, or 5 radical 11, is what we need to write for our simplified radical. Now we're going to use that value as either the base or the height, for which it really doesn't matter. They are interchangeable. Area equals 1/2 base times height, or 7 times 5 radical 11. 7 times 5 is 35, and radical 11 sits tight. 1/2 times 35 radical 11, or 35 radical 11 over 2 units squared, is the area of this triangle. Let's look at example 4 next. Example 4 definitely stands out as being different than the previous 3 examples because we have an angle labeled in the bottom right corner that is not 90 degrees. We are given a 37-degree angle. Since we've been working on trigonometry and that the name of this lesson is actually area and trigonometry, we're probably going to have to utilize our good old friend SOHCAHTOA to figure out this problem. We don't have the height of this triangle. The height happens to be the opposite side with respect to the angle 37 degrees. B equals 4 would be the adjacent side. Whenever you're working with the opposite and adjacent sides of a triangle with respect to a given angle, that requires the use of tangent. In this example, we'll have tan 37 equals opposite h over adjacent 4. Multiply both sides by 4 and we'll get that the height is equal to 4 tan 37. This is actually an exact solution, but to do the calculations, we'll have to find the approximate value in a calculator. 4 tan 37 is equal to approximately 3.01. The decimal is actually much longer, but for the problem on paper, I wrote 3.01, but to complete my calculation, I actually used the entire decimal that was on my calculator screen. Area equals 1/2 base times height, so I'll get that the area is approximately equal to 6.028 units squared for this example. Not every triangle that you're going to be asked to find the area of is going to be a right triangle. This picture, we have what looks like an obtuse triangle, but since these aren't drawn to scale, we don't know for sure. You could figure out the angle measures, but right now we're just focused on finding areas. Since we have our base and height clearly labeled on this picture, we could still rely on this formula. Area equals 1/2 base times height. Area equals 1/2, 3 times 16. 16 and 3 multiply to give us 48, and half of 48 is 24. We could have also found this area by finding half of 16 first, and then multiplying by 3. Half of 16 is 8, and 8 times 3 is also 24. It makes no difference which way you do it as long as you aren't breaking any algebra rules. The area of this triangle, for example 5, will be 24 units squared. Example 6 seems to be a combination of characteristics we saw in example 4 and example 5. Example 4 required us to use trigonometry because we were given an angle measure, one of the acute angles in our right triangle. And example 5 gave us a triangle that wasn't a right triangle. We have the base of this triangle if we look at it carefully. Length 1 plus length 2 makes the entire base. There's no reason why you would need to figure out the left triangle and right triangle separately and then add them. We can do this all at once. We have the base is 11 plus 10, so 21. We have theta, and I'm coloring in this right triangle to the left of my diagram. I can use trigonometry to figure out the height of this triangle. Which trigonometric ratio should I use to figure out the height? If you said tangent, you're correct, because my height is opposite and 10 is the adjacent. Not every example will work out to be tangent. We just happen to see two examples using tangent so far. Tan 28 equals h over 10. Then we're going to multiply both sides by 10 and use our calculator like we did before. Then what we'll do is we'll find the area using area equals 1/2 base times height. You could type everything into your calculator at once if you wanted to. What do I mean by that? Well, you could do area equals 1/2 times 21 times 10 tan 28 degrees. As long as your calculator is in degrees, this will work out just fine. You should also be careful that you're using parentheses and multiplication symbols correctly as well. However, if you chose to figure out the height, 10 tan 28, separately, you should have gotten approximately 5.317. If you chose to do it this way, you'll use 1/2 21 times 5.317 to get your area. Whatever way you choose to do this example, you should get that the area is approximately equal to 55.829 units squared. Example 7 is another triangle that doesn't have a right angle in it, and once again, it appears to be an obtuse triangle. This one has the altitude dropped from the vertex on the top left down to the line that extends out from the base of 9. Our height and our base are still perpendicular, even though they don't actually touch each other. The base is 9 and the height is 8, so this example is actually not bad at all. Area equals 1/2 base times height. 9 times 8 is 72. Half of 72 is 36, so the area is 36 square units. In example 8, we have the same values for our base and our height. The triangle just happens to look different than the previous example. Looks could be deceiving, but since we'll fill in 9 for base and 8 for height yet again, we're actually going to get 1/2. 9 times 8, 1/2 of 72, 36. We're going to get 36 units squared for the area of the triangle again. More than one triangle can have the same area, so don't feel insecure or doubt yourself. As long as you're following the rules, you're good to go. Example 9, while definitely not drawn to scale, also has 8 and 9 labeled. However, while the 9 is still the base of my triangle, 8 is no longer the height of my triangle. It's just another side. If I want to find the height, which seems like I do want to do that, the entire worksheet I've been using, area is 1/2 base times height, I need to be creative. 1/2 is good, 9 is good for my base. How can I figure out the height? Well, as you're brainstorming, it would probably be in your best interest to draw in your height with a dotted line. Now that I have this altitude drawn in for me, I have a right triangle on the left side. I like this right triangle better than the one on the right side because I already have one of the acute angles labeled. I'm going to redraw this particular right triangle on the side so I can concentrate on the parts that are really important to me right now. One major announcement that I really think deserves a lot of attention is this bottom leg is not 4.5. It is not half of 9. I don't care if the picture looks like it's half of 9. It isn't. Unless you know you have an isosceles triangle, you don't know what portion of that full 9 the left side is. However, we do know for sure that side A is equal to 8. That one we definitely know. We also know angle C is definitely 40 degrees. If I have 40 degrees and I have the hypotenuse of a right triangle, which is 8, and I'm looking for H, which is the opposite side with respect to the 40-degree angle, which trigonometric ratio should I use to calculate the missing side? I'm looking for H. The trig ratio I'm going to use to figure out the height in this triangle is sine. The sine of 40 degrees will be the opposite over hypotenuse, which will be H over 8. To get H alone, we're going to multiply both sides by 8. The height of the triangle is 8 sine 40 degrees. While this is an exact answer, to figure out the approximate decimal value, we are going to use our calculator. The approximate height will be 5.3 1423 units. Again, I'll leave the full value of this decimal on my calculator screen. Then, to find the area, I'm just going to multiply it by 1/2 and 9, or by 4.5. After using a calculator to find the area, I get that we have an area of approximately 23.14 square units. The triangle that we just worked with in this last example, if you look carefully, is actually a situation where we're given a side, angle, side. Whenever we have a triangle with these conditions met, a side, angle, and side, all consecutive in a row along the perimeter or the outside of my triangle, I'm going to be able to use a special formula that we'll be deriving in example 10. When you're trying to figure out the area of a triangle and you want a general formula, you really want to make sure you're using letters or variables and not numbers. I'm creating example 10 to look exactly like example 9. However, I'm not going to have values filled in. A, B, and C are the letters I'm going to be using for this situation. My base is going to be B, so again, I'll have 1/2 times B. The height is still the piece that's missing, so I'm going to figure that out in general using trigonometry. I'm going to drop an altitude yet again, and I'll label that H. The sine of C will equal opposite over hypotenuse. The opposite will be H, and the hypotenuse will be A. If I solve for H, I'll do that by multiplying both sides by A. That means H equals A times the sine of C. If I fill A times sine C in for height into my area equals 1/2 base times height formula, I will get area equals 1/2 B times A times sine C, or I could rearrange the A and the B so they're alphabetical, and I'll have area equals 1/2 A B sine C. So let's look at this one more time quietly, and hopefully you can think about how I explained it before and understand where that formula came from. I'm also going to rewrite the formula using letters in a different order, 2 different ways. So you'll see area equals 1/2 AB sine C, area equals 1/2 BC sine A, and area equals 1/2 AC sine B. I'll also write this equation using words to describe sides and angles, since some people learn better that way. Take your time copying this. This formula comes in really handy, and it's actually much quicker than Heron's formula if you have a side, angle, side triangle. Heron's formula we would reserve for a side, side, side triangle.